Every year, the Global Carbon Project (GCP) puts out a nice detailed report on the carbon budget for the previous decade or so. You can only do these averaged, even though they estimate annual numbers, as we'll see in a minute. And I like to read it just because it makes some good points about what we are doing okay with and what we are not able to manage in terms of reducing emissions. Obviously, we are still not bending the curve, but without getting too pessimistic, let's read the science part of it. Accurate assessment of anthropogenic carbon dioxide emissions and their redistribution among the atmosphere, ocean, and terrestrial biosphere in a changing climate is critical to better understand the global carbon cycle, support the development of climate policies, and project future climate change. Here we describe and synthesize datasets and methodologies to quantify the 5 major components of the global carbon budget and their uncertainties. Fossil fuel CO2 emissions, EFOS, are based on the energy statistics and cement production data, while emissions from land use change, ELUC, are based on land use and land use change data and bookkeeping models. So there are always some models involved, and there are uncertainties on each of these estimates. Atmospheric CO2 concentration is measured directly, and its growth rate G-atma is computed from the annual changes in concentration. This is something we can do very precisely and accurately because it's well mixed, inert, and easy to measure in some ways. Of course, when you do global mean, you have only hemispheric gradient to worry about, so it's easy to handle atmospheric CO2. The ocean CO2, on the other hand, is estimated with global ocean biogeochemistry models and observation-based FCO2 products, which are the partial pressure differences or partial pressures. The terrestrial CO2 sink, SLAND, is estimated with dynamic global vegetation models. Additional lines of evidence on land and ocean sinks are provided by atmospheric inversions, atmospheric oxygen measurements, and Earth system models. Sum of all sources and sinks results in the carbon budget imbalance, missing sink, if you will, a measure of imperfect data and incomplete understanding of the contemporary carbon cycle. All uncertainties are reported as ±1 standard deviation. Just in terms of numbers, for the 2023, EFOS increased by 1.3% relative to 2022, so fossil fuel consumption and emissions went up, with fossil fuel emissions at 10.1 gigaton carbon per year, when the cement carbonation sink is not included. The land use was 1 gigaton carbon per year, with a fairly large uncertainty for a total anthropogenic CO2 emission, including the cement carbonation sink of 11.1 gigaton carbon per year. And you can also do that as CO2, so carbon and CO2, 3.7, whatever the number you multiply with. Also for 2023, the growth rate was at 5.9 plus minus 0.2 gigaton carbon per year. S-ocean was 2.9 gigaton carbon per year, and land sink source was 2.3 gigaton carbon per year, with a near zero balance, residual essentially in the carbon budget. The global atmospheric CO2 concentration averaged over 2023 reached 419.3 ppm with some small uncertainty. Preliminary data for 2024 suggest an increase in EFOS relative to 2023, so we continue to burn more fossil fuels. Globally, an atmospheric CO2 concentration increased by 2.8 ppm, reaching 422.5 ppm, 52% above the pre-industrial level of 278 ppm in 1750. Overall, the mean and trend in the components of the global carbon budget are consistently estimated over the period of 1959 to 2023, with a near zero overall budget imbalance, although the discrepancies of up to around 1 gigaton carbon per year persist for the representation of the annual to semi-decadal variability in CO2 fluxes. Comparison of estimates from multiple approaches and observations shows A persistent large uncertainty in the estimate of land use change emissions, not very difficult to imagine because of all the hyperlocal scale impacts, and low agreement between the different methods on the magnitude of the land CO2 flux in the northern hemisphere extratropics, and thirdly, a discrepancy between the different methods on the mean ocean sink. Ocean also is largely unmonitored, and models estimated, but model uncertainties are there, of course, right? So this is atmospheric CO2 concentration with NOAA measurements going here from 1980 onwards, and the Keeling curve before that. So you can see that we continue to rise and we are not bending the curve. There are some details here that you can read up. This is an interesting figure that always gives a lot of information. So this is the global carbon cycle, and you have to be sure that this is average. So schematic representation of the overall perturbation of the global carbon cycle caused by anthropogenic activities averaged globally for the decade of 2014 to 2023. This is important and necessary because in each year you don't get a very good sense of the global carbon budget and perturbations. Things are still, evolving on that time scale. So here we have 9.7 plus minus 0.5 gigaton carbon per year in terms of the anthropogenic or fossil fuel CO2 EFOS. And then you have lots of other numbers like gas reserves, oil reserves, coal reserves, which are estimates. And then you have permafrost doing its thing with basically what it's taking up and what it's emitting are very similar. Vegetation in gigatons, soil carbon, this is at 450, this is at 1700. So there are standing stocks and there are fluxes. So there is downward flux sink of 3.2 gigaton carbon per year over here, and you have rivers and lakes doing their thing. Coasts have 10 to 45 gigaton carbon, so large uncertainties or range at least. Surface sediments 1750, organic carbon 700 gigaton, and ocean also takes up and emits large numbers, but net sink of 2.9 gigaton carbon per year, as we said. Marine biota has about 3 gigaton carbon, and dissolved inorganic carbon in the ocean, the largest pool at 37,000 gigatons carbon. And of course, atmosphere is seeing a growth rate of plus 5.2 gigaton carbon per year, and the standing stock is now at 890 gigaton of carbon. So usually it's double of the concentration, which is at 419 ppm. So those are the numbers, and you can also look at the annual carbon emissions over time from 1850 onwards. Fossil fuels continue to increase with little dips for financial crises, COVID, and so on. Net land use, and there is a land sink as well. So land overall is now emitting a little number that we saw here. 3.2 downward, so that's the land, and you can see that this is smaller than this here, land sink in green. Atmospheric growth is shown here, so you can see this dashed line is basically the missing sink or the budget imbalances or residuals, and the ocean of course continues to take up more, and the worry is always about whether land and ocean will continue to take up and keep the carbon, or is the warming going to make them become net sinks instead of net sources instead of sinks as warming continues. Okay, so cumulative carbon emissions are also shown here. I won't read the numbers, but these are important because in real world, in the models, you see that the warming is linearly proportional to cumulative carbon, which means you can track how much more CO2 may be left in terms of staying below 1.5 degrees C or 2 degrees C, and so on and so forth. Okay, so let me clarify. Yeah, so I wanted to clarify that FCO2 is not just partial pressure, it's fugacity, which is related to partial pressure, but the non-ideal behavior of the gases have to be considered as well. Okay, so it's just a slight detail you should remember. I said partial pressure, which is not exactly right. Okay, so let's leave this here.